Hello guys, Assalamualaikum warahmatullahi wabarakatuh and a very good day. So today I'm going to teach about electrochromic supercapacitor. So a new multi-functional energy storage device. Okay, so what is electrochromism? So electrochromism is the ability to change color on a small potential of light. So the material that have the ability of electrochromism means that the material have a redox properties which capable to change color upon a small potential of light. Next is supercapacitor. Supercapacitor is a device that have the ability to store charge. So in order to have a multifunctional energy storage system, you should have a supercapacitor with redox behavior, either battery type or pseudo capacitor. So now you already know about what is electrochromic and also what is supercapacitor. Okay, let's move on to the electrochromic supercapacitor. What is electrochromic supercapacitor? So in one device, it shows color changes and also at the same time, it can also store charge. So that's electrochromic supercapacitor. This is the example of the electron from light color to dark color. From the process is the charging process. So this is bleaching and this is the coloring. So let's see the first video. Okay, as the first video, you can see I play the first video. When we charge the material slowly, you can see the color become darker and darker. So at one time, it become very dark when the potential window is the maximum. So it is important for that material to have the capability, means that the capability to have the color changes when we are doing the electrochromic supercapacitor. Means that when you are charging, it's changed to darker color. When you discharging, it's become bleach, the color become lighter. So one of the application it can be implemented in the smart window technology. Let's see, we can move forward. Okay, this is the color become very dark. Okay, and in the end we discharge the color become lighter. Okay, so let's see the second video. Second video is more like the color. Okay, we start charge the process here. You can see it's charging, and then with discharging, it's become colorless, and recharging again. The color become black, slightly brownish. Okay, that's the ability of the material to undergo electrochromic supercapacitor. Okay, next is the analysis that you need to do for an electrochromic supercapacitor. The first analysis is what we call that in situ absorbance, where you have two apparatus. One of them is potentiostat. Okay, on the potentiostat, if it's equipped with the potentiostat, then you run the absorbance at different potential window. This is from 0 to 0.5. Then we measure the absorbance difference of the material, because we know that absorbance will show higher intensity if the color is very dark. So that's why at 0.5 volt the color is darker. That's why the absorbance is the highest. For transmittant is the opposite of the absorbance. When you have a darker electron, the transmittant is the lowest. Then from that, both absorbance and transmittance is an in situ. What we call that? We are doing it in situ during the experiment, so we call the results. Means that when we giving the voltage, for example, is 0 volt, so we measured the transmittant and absorbance. Same when we apply the potentiostat at higher voltage, for example, is 0.5 volt, and we measured the absorbance and transmittance simultaneously. Next is the charge. We can also calculate the charge. Over the time, you can see that the charge increases, and from this charge, we can calculate the CE, which is the coloration efficiency. I will not show, so I show it in the other video about the coloration efficiency. Okay, next is about the kinetic study. So transmittant versus time, whereby we measured the transmittant when the sample in charging. So in charging, the color is darker, so transmittant is lowest. Okay, this is charging, and this one is discharging. When discharging, we are bleaching the process, and the transmittant is the highest. So we alternate between charging and discharging at certain wavelength, at a fixed wavelength. Okay, so what we can get this DC, which is the coloring time, about 17.57 seconds, and also the bleaching time is 13.51 seconds. Okay, delta T is the optical contrast, the difference between the transmittant at the highest and the lowest. Some said 95% highest and 95% lowest. That's the meaning of optical contrast. By having the optical contrast, we proceed to the next analysis, which is the retention of the optical contrast to measure the capability of our material. Either the material can retain the changing of color, because we know that the process of redox is very fatigue. It gives iteration and regression to the electrode material, so the electrode become fatigue and the stability cannot be retained. That's why we measured around with a number of cycles to 1,000 cycles to see the capability of optical contrast retention of our material. And last but not least, we provide the data for the first cycle and also 1,000 cycle. You can see the transmitted versus time spectra to see the difference, because the capability of the device is to give 85.57%. So we need to increase more to be implemented into a real device application. So I think that's all. Thank you very much. Thank you for watching.